In the previous video, we started to talk about the 3D graphic capability provided by Matlab, right? We looked at a few commands, well, a few functions, right, which allows us to plot lines and points in 3D, like plot 3, and then make surface plots, right, using mesh and then variations of mesh Z and mesh C, and then surf and variations of surf L and surf norm, right? And then we looked at some basic usages of the color map, and we looked at some two arbitrary examples provided by Matlab actually. This time let's look at the contour plots. Right. So how do we actually make contour plots? So again, let's try to create some kind of fake data set, right? So what I'm gonna do is that so peaks is a Matlab intrinsic function that comes with Matlab, and it's gonna create the output of the peaks function. If you actually give it a no input, then it's gonna try to actually create so it's not giving, it's not, you don't have to give it any kind of inputs, right? But it's going to create three outputs, x, y, and z, right? X and y are going to be two-dimensional meshes, and then z are going to be the vertical value for every two-dimensional nodes that's defined by x and y, right? So if you have let's look at the help page for peaks, right? A sample function of two variables. It's a function of two variables obtained by translating and scaling Gaussian distributions. So basically, it looks like a Gaussian, basically, but it's two-dimensional Gaussian, right? Which is useful for demonstrating mesh, surf, pcolor, contour, etc. Right? We looked at mesh and surf, and we didn't actually use peaks as the sample dataset, but we are going to look at the pcolor and contour by using the peaks. So we're going to look at pcolor in just a little bit, but let's look at the contour first, right? Contour. Let's try to so we're going to use peaks to create x, y, and z, right? And then let's try to create a figure 9. Let's say figure 9, right? Do I have a figure 9? Let me check. So last one was like figure 8. Okay, so I don't have a figure 9. Let's use figure 9. And this time we're gonna use subplots. We're gonna use a 2-row, 2-column subplot, and in the first subplot we're gonna do a contour. Right. So this contour function just like its name suggests, it's gonna draw contour lines. But how many contour lines you want to draw, right? By default, it's gonna draw like 10 contour lines, right? But the last input is gonna specify how many contour lines you want to draw, right? So here we're actually asking Matlab to actually draw 30 contour lines here, right? You can adjust this number if you want a denser contour, right? Let's just run this piece of code. Right. So that's what this contour plot actually looks like, right? You can sort of imagine it's got like a two. This is the peak, right? But this is actually a trough. This is two smaller peaks, right? This is a smaller trough, and then you might have another trough that's kind of in the middle. If you actually have the patience to actually count how many contour lines you have, it's exactly 30, right? So if you want a denser contour plot with lots of contour lines, then you can, all you have to do is to actually increase the last number, right? Make it bigger, so you get more contour lines. Okay. Let's try to adjust the color map. Right. Let's change the color map jet, right? So this way it's gonna give us a better view, right? It's either red or blue or that kind of thing, right? So making the contrast bigger. So this is for generating 30 contour lines. Right. And then subplot 2-row, 2-column is the second subplot, right? And this time we're going to try to actually create three-dimensional contours, right? So this is a three-dimensional plot in the sense that the color of the lines actually indicates the third dimension, right? Even though it's drawn on a two-dimensional coordinate system, but the color is used to actually indicate the third dimension, right? So in essence, this kind of contour plot is actually a three-dimensional plot. But Matlab also provides another thing that's called contour 3, another function that's called contour 3. That's exactly drawing contour lines in 3D space. Right. So let's still do x, y, z, and 30. Right. So that's gonna give you this kind of contour lines, right? So not just the color, but also the location of the contour lines are kind of positioned at the correct z value, right? So if you actually take a map view, it's not this button, it's this button. If you actually look at the map view, then it's gonna look exactly like the two-dimensional contour, right? Right. If you look from the top, that's gonna be exactly the two-dimensional contour plots, right? But it's got a perspective, right? But it's if you look from an angle, then it's gonna display the contour lines in three-dimensional space, right? It's actually quite cool, right? That's contour 3. That's contour 3, right? It's probably a better idea for me to actually make this figure undocked. So if we sort of look at this kind of figure in a, if we make the figure slightly bigger, then we can sort of see the effect a bit better, right? So it's giving you a clearer view about how the contours are actually being drawn in three-dimensional space, right? And that's contour 3. And then let's look at another variation of contour plot. And then let's plot it into the fourth subplot, right? It's called contour F. Contour F means fill. This time let's just use like 15 contour lines, right? So it's gonna try to actually fill the space between neighboring contour lines with the color, with a specific color, right? And the color is actually determined by the value that's kind of between the neighboring contour lines, right? So you can sort of see the region with the highest value is going to be plotted with the red color, but the region with the lowest value, the z value, I mean, is going to be plotted with the coldest color, right? That's what's specified in the jet in the color map, in the jet color map, right? So so that's contour F. F just means fill, so it's gonna try to actually fill up all the different white spaces, right? All the different white spaces with the correct color, with the color that's gonna reflect the value of the z coordinates, right? I still have one more space here, right? One more subplot space here. But in this subplot, I'm gonna try to demonstrate another function. It's not contour, but it's not contour function, but it's a different function. It's called pcolor. Right. So what exactly does pcolor mean, right? Pcolor means pseudo-color, right? It's got a weird name. It's called pseudo-color. called a pseudo-color or checkerboard plot, right? So what does it do, right? It's more or less like the image function. It's more or less like the image function, except that it's gonna try to so the input is still just a matrix, and inside of this and the values inside of this matrix is gonna be plotted using a specific color map, right? So if you are using this jet color map, then every element inside of this C matrix, if it's got a value, right? If it's got a value, and then that value is going to correspond to a particular color inside of that color table. By just the color table is merely just a lookup table, right? So if you got a lookup table means that every value is going to correspond to a particular color, basically, right? A color is just RGB, right? RGB, red, green, and blue, three colors that's kind of mixed together, right? So every value inside of the C matrix is going to be mapped to a particular RGB triplets, right? According to this kind of a color map, or that's called a jet here because here we're actually using jet as the default color map, right? And then pcolor is just gonna sort of plot that particular color at the correct location, right? So let's take a look, right? For now, it's not gonna look very pretty. It's not gonna give you the correct effect because you're gonna see all those grid lines, right? You're gonna see all those grid lines. So if you want to turn off the grid lines, what you have to do is to change the shading. So by default, the shading is a patch, so it's gonna draw those grid lines. But if you actually do shading interp, then it's gonna remove all the grid lines. Right, so now it's gonna give you a relatively smooth looking pcolor plot, right? If you want to put the box on it, put a surrounding box on it. For some reason, it's not taking effect. Why is that? But anyway, that's maybe. And then we can hold on to it, right? And then we can sort of do another contour, like 15 or something. Right. For some reason, it's not giving me. Oh, I see. Because the contour lines are not exactly black lines, right? It's gonna the contour lines, the color of the contour lines are gonna sort of blend together with the background, so you won't be able to actually see those lines. But anyway, it's this piece of code is no good, right? But that's pcolor. That's pcolor. It's again by using the color to actually indicate the z value. So essentially, it's a three-dimensional plot. The contour function actually creates some kind of output, right? So if you look at the user manual about contour, it's going to create some kind of output for it, right? So how do you actually use that kind of output? For now, we are not really using it, right? So let's try to use the output. Let's create another figure 10. Right. Let's try to actually use the output of the contour function, right? 2 row 1 column, the first plot. C gonna equal to contour x, y, z. Let's give like 12 contours, right? So in principle, it can return 2 outputs, right? C and H. Here we're just using the first output. We're ignoring the second output, right? It's saying that it's a contour matrix C. So basically, C is going to be a two-dimensional matrix, right? And then inside of this matrix, it's gonna store all the different contours, right? So but how can you actually use this particular matrix, right? So for now, all the contours don't have numbers that's kind of marked on it. We don't really know what's actually the value, right? If we want to know the value, we have to sort of look into the color map, right? If we have a color bar that's right next to it, then we can actually look at the color and then try to guess what's going to be, try to estimate what's going to be the value that's lying on this particular contour, right? Um, So now let's try to use this contour matrix, right? So first let's try to execute this piece of code first to create the figure. So now we have a two-dimensional we have the 12 contours, right? And now let's try to use the C matrix, the contour matrix, right? So how are we going to use it? We're gonna use this C matrix to actually put labels on those contours, right? So how do we actually use add labels to contours, right? There's a Matlab function that's called C label, and then it's gonna take this C matrix as input, right? If you haven't used the C label before, it's called color label basically. So, right. So it's gonna insert rotated labels into each contour line, and the contour line must be long enough to fit the label. Otherwise, C label does not insert a label. So C, it's gonna take two inputs actually. C and H are the contour matrices, and then the contour handle, contour object handle, right? That's kind of created as the output from the contour function or contour 3 function or contour F function. Every variations of the contour function is gonna give you this kind of outputs, and then you can use that output uh, to as the input to the C label function, right? So let's just use the okay. So now you can sort of see the numbers, right? Those numbers are actually giving you a specific value, the actual value for each of the different contours, right? Um, so you can also see there's some more detailed explanation about the symbols, right? So sometimes you see this kind of plus sign, that kind of thing, and sometimes you may see some small minus sign, that kind of thing, right? Let me blow up the figure, right? If I make the figure bigger, right? And those kind of symbols actually has a specific meanings, right? And it's a um, so it's related to the mode. It's related to the mode of the label placement. Is it inline or some kind of inline and this kind of plus symbol, right? Um, that's gonna um, determine the orientation of the text, basically, right? So um, but this is just by using the contour matrix C, right? But we can sort of see we can also create a output, handle output that's gonna allow us to actually access the individual contours, right? So let's use two outputs. C and H is gonna equal to contour X, Y, Z, and 12, right? And then we can call C label again. C and H, right? And then so C label also takes the contour handles as the second input. And then for the third input, we're gonna use the so-called label spacing. So what we want to do is to make sure that the individual labels, for now, some of the labels are kind of clustered together, right? Which makes it really difficult to see. This label spacing option allows us to actually specify the kind of spacing between neighboring labels. So that's gonna allow us to actually see better. Right. So this time you can sort of see there's no plus sign, right? There's no plus sign, which means all the labels, the numbers are gonna be kind of aligned with the direction of the contour line, right? So all those labels, all those numbers, are not exactly like a line horizontally, right? It's gonna have an angle that's kind of aligned together with the contour lines, right? So maybe that's a better effect, or maybe this is a better effect, right? Depending upon your specific application. Right? So that's how you can actually use the outputs uh, from the contour function, right? To create to plot the labels on top of the contour lines, right? Those are kind of some examples of the of some of the commonly used or widely used three-dimensional graphic capabilities, right? So contour plots, surface plots, mesh plots, pseudo-color plots, all those kind of plots are used very widely, right? But now let's look at some of the less well-known 3D plots. Let's call it special 3D plots, right? Some of the functions might be useful for very special applications, right? Let's create another figure 1, right? The first one we're going to look at is called waterfall. And then let's see what's actually the waterfall figure actually looks like. Right? It looks like that. Looks like that. Exactly like a waterfall, right? And the lines are going to be like drapes. Are going to be like drapes that's plotted across a certain direction, right? If you want to sort of rotate it, right? That's called a waterfall plot, right? And then let's look at another one called a ribbon. But I'm just using Y and Z, right? And then let me change the shading to interp. Right. Let me just execute these 3 lines of code. Right. That's more or less like a waterfall, but instead of just drawing lines, it's gonna draw thicker ribbons, right? It's not exactly lines anymore, it's ribbons. And you can sort of imagine why I neglected the X here, right? Because X is gonna sort of just go from like a first point to last point or something, right? It's just gonna go horizontally. Okay. It's a special purpose plot, right? It's called a ribbon. And then sometimes we might want to visualize the so-called gradient. When we make the surf plot, there's a variation that's called a surf norm that's going to plot the normal direction. Using those red sticks, you can actually visualize the normal direction, right? Uh, that's kind of perpendicular to the surface, right? Right. That's kind of perpendicular to the surface. There's another way to actually visualize the gradients. That's called quiver. But in order to actually do this kind of experiment, we need to first of all let's create a slightly denser xyz from the peaks function. But this time we're going to use 32. So that's going to give us a mesh that's kind of denser than the default values. And then we can just use we can compute the gradient. Gradient is more like the derivative, right? But a derivative in a one-dimensional function, so y equals to fx. If you have just a one independent variable, then the derivative is just a dy dx, right? Dy over dx. But for a two-dimensional thing, for example, z equals to fxy, right? Then you're gonna have two derivatives, right? One is partial z over partial x. The other one is partial z over partial y, right? And Matlab actually provides you a function for you to actually compute this kind of a derivative. That's called a gradient, right? Z. And then you can specify the horizontal, the interval, the spacing of neighboring grid points. So it's a numerical approximation to the gradient. So let's give it a 2.5.25. That's kind of the spacing between neighboring grid points, right? And then we can contour x, y, z, and then let's give it like 10 contours, right? And then we can hold on to it, and then we can use the quiver function, x, y, and then minus dx minus dy. So gradient is actually the direction that the function is going to increase fastest, right? By joining the negative minus dx minus dy, it's going to show the direction of the steepest descent. It's going to show the direction of fastest decrease in the z value, right? Right. So this is plotting using the quiver to plot the gradient on top of the contours, on the background of contours. So you can sort of see, so arrows flows into this low, flows out of this high, right? This is a high, right? This is a low, right? Z value is large here, Z value is small here, right? And then arrows flows out of the high, and then flows into the low, right? And then the length of the arrow is going to be proportional to the length of the gradient. So if the gradient is really strong, which means the slope is really steep, a very steep slope, then the arrows are going to be kind of longer than locations where the slope is kind of smooth, right? It's not so steep, right? It's called a quiver. It's called a quiver, right? And this quiver function also has a three-dimensional version. It's also got a three-dimensional version, right? So let's still x, y, z equals to peaks. Let's use slightly fewer points, and then x, and y, and nz. So we have used the surf norm to make the plots before, right? But surf norm can also create normal directions as outputs, right? So nx, ny, and nz are going to be normal directions in 3D normal directions, right? So surf, let's still use surf to plot x, y, plot the surface first, and then we can hold on to it, and then we can use quiver 3. That's sort of the three-dimensional version of quiver. X, Y, Z, and then NX, NY, and then NZ. Right. And then let's execute this piece of code. Right. Right. So this is not exactly the gradient plot, right? It's not a gradient plot. So here quiver is actually plotting the gradient, but here quiver 3 is actually plotting the normal direction. It's plotting the normal directions. So it's not exactly the the directions of the steepest descent anymore, but it should be directions that's kind of more or less perpendicular to the local curvature, right? But again, the scale of the horizontal and vertical axis are kind of different, right? So if you actually look at the plot in the if you actually make sure that the scale is exactly the same on each of the directions, then all those arrows are supposed to be perpendicular, exactly perpendicular to the local curvature of the surface. But let's still change it to axis normal, right? That's quiver 3. That's quiver 3. And then there's another special purpose plot that's called stem 3. When we did the two-dimensional plot, we looked at some special plots that's called some of them. We looked at the several functions that's going to give you sort of bars, pie charts, stem plots, stair plots, right? And then stem also has its three-dimensional version called stem 3, and then it's going to give you this kind of effect, right? So it's going to give you lots of sticks, right? And then with the circles on top of it, right? And the height of the stick, also the location of the circles, are going to be dependent upon the z value of the particular function, right? That's a stem 3. And then one last thing that I want to talk about is transparency in 3 dimension, right? Transparency. So how do we actually handle transparency in 3D, right? So again, let's look at one example. Right? Let's look at one. This time we're going to try to create some kind of a shape that resembles the shell of a snail, right? So again, it's a parametric surface. So let's try to create some kind of a parameters. 1.13 b equals to 1.14, and then uu equals to link space 0 2 times pi 120, right? And then vv is going to equal to link space 0 it's not 0 to 2 pi, it's minus 15 to 6, and then 180, and then u and v is just gonna create a mesh grid uu and vv, right? And then x is gonna equal to a dot hat v dot multiply cosine of v dot multiply 1 plus cosine of u, right? Y equals to minus a dot hat v dot multiply sine of v dot multiply 1 plus cosine of u, and then z equals to minus b times a dot hat v dot multiply 1 plus sine of u, right? And then let's create a figure 16, right? Figure 16. H equals to surf x, y, and z, right? Set H. So this time we're not just making the plot surf, right? We're asking surf to actually return a handle to the surface that it actually creates. And then we are using the set function to configure the properties of this particular surface, right? Face alpha, right? And then let's give it like 0.4. Let's just run this piece of code, right? So it's gonna create this kind of a graph, right? Looks like the shell of a snail, right? If you actually rotate it, right? And the reason that you can see through it, you can see the interior of it, is because the face alpha is set to 0.4, so you have some transparency to it, right? You have some transparency to it, so you can see through it. But now let's try to get rid of the grid lines. For now, you can still see the grid lines, right? Um, uh, so how do we actually get rid of the grid lines? Shading interp is going to allow us to actually get rid of the grid lines, right? Right. It's going to get rid of the grid lines. But another thing that you may have noticed is that as I drag this particular plot and rotate it in space, the dimension of the axis, the scale of the axis actually changes together with the orientation of the shell of the object, right? That's something that's kind of undesirable, right? When we rotate the object, we would like to have the scale of the coordinates, or the scale of the three axes, to be fixed in space, right? Instead of adapted to the view, right? So how do we actually do that, right? There is another command that's called axis. We have used the axis equal, axis tied before, right? But there's also another option that's called vis3d. We want to turn vis3d to be off, and then we want the scale to be equal, right? So let's evaluate this selection, right? And then if we actually rotate it, the color scale is not gonna change, right? So it's actually three options, right? vis3d off and then equal. So it's equivalent to typing axis vis3d and then axis off and then axis equal. So axis off is gonna get rid of those explicit plots of those three axes. You don't see the three axes anymore, right? And then axis equal means just the scale for the x, y, and z axis are gonna be identical, right? Axis vis3d is something that we haven't seen before, right? But you can actually take a look at the help page of axis, and then it's going to tell you vis3d. It's going to freeze aspect ratio property to enable rotation of 3D objects and overrides stretch to fill, right? That's actually a critical thing, right? So if you do not use axis vis3d, then it's gonna the plotter is going to be adapted to the particular view. It's going to try to actually stretch to fill. It's going to try to actually stretch the object in a certain directions in order to actually fill up the entire plotting window, right? But by doing axis vis3d, it's going to override. It's going to override the stretch to fill property of the stretch to fill behavior of Matlab. So now if you actually rotate it, the aspect ratio is not going to change, right? That's actually quite a useful. That's actually quite a useful thing, right? And then let's just use this particular example to look at one more command that's called view, right? So view is also a function that's going to control the viewing angle. It's going to control the direction in which you want to view this particular object, right? So if you type help view, then it's gonna show you how to use this particular function. It's actually going to take two numbers, or a vector with two numbers, which is called azimuth and elevation, right? Which are basically two angles. Azimuth is an angle, but elevation is more like elevation is also an angle actually. So azimuth is the angle of your viewing point from x-axis, right? And then elevation is sort of the vertical angle of your viewing angle from the horizontal plane, basically. So azimuth equals to 0, elevation equals 90 is directly overhead and a default 2D viewing angle, right? 2D viewing angle. So view 2 is gonna set the default 2D view. That's AZ equals to 0, elevation equals 90 degrees. And view 3 is gonna set the default 3D view. That's azimuth equals to minus 37.5 degree, and elevation equals 30 degree, right? So let's try to come up with let's use minus 35, right? That's gonna be our azimuth, and then our elevation, let's give like 38 or something, right? Right. Let's just run this line of code. Right. Then that's gonna give us this particular angle of the view, right? Of course, you are still allowed to actually drag and rotate it, right? Right. But if you want to sort of look at the particular object at a specific angle, view with the two input parameters allows you to actually fix your viewing point at those specific angles, right? Specific azimuth and a specific elevation. Okay, so that's three-dimensional transparency.